So now we're going to get into the basics of population ecology. Now, some background information before we keep going too far. We do want to remember from our last unit what evolution is, and that it does not affect individuals. We're looking at change occurring over time within a population, and it's not going to change an individual's genome, right? So an individual's genome is going to stay pretty much the same throughout their lifetime. We're not going to see changes happening there. We're going to see changes happening within a population, both in things like allele frequency, which is microevolution, and large-scale, potentially speciation changes, which is going to be macroevolution. So what types of factors can affect populations but not the individuals? Things like natural selection, allele frequency change, birth and death rates, and immigration into or emigration out of a population. Now, in a stable population that's neither growing or shrinking, basically 2 offspring will survive to replace their parents. So this is straight up just pure replacement. It takes 2 parents to make the offspring, and so if these 2 parents have 2 offspring, then we have basically just replaced the parents when they die. The growth rate is the change in number of individuals in a population over a defined period of time. So we're looking at how has the population changed in numbers? Has it grown in population? Has it shrank in population? Or has it stayed about the same? And so the growth rate will tell us that, how much it's changing over time. Is it growing really, really fast? Is it shrinking? How fast or slow is it shrinking? Or is it pretty much stable? So when the birth rate outweighs the death rate, meaning we're having more births than we are deaths, then a population will grow. If the death rate outpaces the birth rate, so more individuals are dying compared to those being born, a population shrinks. Now, exponential growth is a type of growth that can occur when resources are unlimited. It's important to note that we don't really truly have unlimited resources, but if you are in that phase, if a population is in the phase where they have well over the number of resources they need to support their population, they can experience what's called exponential growth, which is basically an explosion of growth. You're seeing growth that happens it seems to be slow at first, but once it gains speed, once it gains steam, then it grows very, very quickly. So basically the larger the population gets, the faster it grows. So growth is proportional to population size. As the population gets bigger, then the population grows faster. Now we also want to measure how many individuals are in a given area. So the number of individuals in a given area is called the population density. Now, like I said, there are no truly unlimited resources really. There's going to be some resource that ends up being like the limiting factor in any population's growth. And so what we see is that as populations grow, those resources start to become depleted and growth is forced to slow down. And so once we've reached that capacity, we've reached that limit of the resources that are available, we say we've reached the carrying capacity, which the carrying capacity is the maximum number of individuals of a population that a certain area can support. What that carrying capacity is, it's going to be different depending on which type of organism you're looking at. So the carrying capacity in a given location will be different for things like the insects compared to the herbivores, compared to maybe a top predator. It's looking at what resources that population needs, and pretty much you're always going to be limited by the most limited of those resources. One of those resources is going to be considered more scarce than the others, and that's usually the one that's going to have the biggest impact on the carrying capacity for that population. Now, there's a few different types of factors. We can have density dependent and density independent factors. Density dependent factors limit population growth as the population increases. And so a lot of times we're thinking of things like resources that are available. So you only have so much food available. And if you have too many individuals in a given location, then you're going to run out of food. Same thing with reduced space. There's a finite amount of space. And so if you have a population that grows really rapidly, some individuals may be left out in the cold. They might not be given that space. There's also an increase in diseases or parasite risk. And this is because, especially among infectious diseases, when you're closer together, when the population is more dense, it's easier to spread things around, right? And that's something that we saw with COVID-19 to some degree, that in cities or in areas where people had to be packed together and they didn't have a choice, that they're around people, that increased how many people got sick. But if you have less contact with other people because you're more spaced out, or if you're properly socially distancing and quarantining, then we didn't see that increased disease risk. And it doesn't apply to humans really, but when we look at things, especially like herbivores, things that usually turn out to be prey items, we see that when you have a highly dense population, predation usually increases too. Now, logistical growth or logistic growth is usually what we see when we're looking at any population, because it's exponential at first since the resources are widely available for the given population, but as our population grows, it begins to level out on the top because we've reached our carrying capacity. Now, some factors that affect population have nothing to do with density, and so those are called density independent factors, because it doesn't matter how big the population size is. So usually you think of things that are geology based or weather based, things that are just kind of like bad luck for a population. Consider something like a hurricane coming through. When a hurricane comes through, it doesn't matter if you're in a big city or a small town, a hurricane is still a hurricane and it's still going to cause damage and affect that population. And so here we see the exponential growth in this kind of pale teal, and then the logistic growth. And so we see that the exponential growth, this is what would happen is if the resources were truly unlimited. But we know that that's not the case, that at some point in time, food, shelter, mates, something is going to limit how many individuals can exist in a given location. And so we usually see what we call logistic growth, where we grow and we get faster as the population grows, but as we start running out of resources, growth slows down. And so we end up reaching that carrying capacity, which is shown here in orange with the letter K. And it kind of tapers off and stops. And it's going to stay there because anytime you go over it, individuals are going to die out because they don't have the resources that they need. Now, sometimes population growth can be explosive and rise rapidly at random intervals. When we look at short periods of time, population growth can look like it's fluctuating. But if you look at the bigger picture, you look at a much longer time frame, then it does even out. This is typically like the exception. The explosive growth is usually the exception rather than the rule, because logistic growth describes most of the population growth we see. Now, when it comes to resource management, there's a major concern with determining the maximum sustainable yield, or the maximum number of individuals of a population that can be removed without impairing population growth. And it's about half of the carrying capacity. Now, you're not going to draw anything, but this is something, especially when we look at fishing or hunting, things of that nature, when we pull individuals out of the ecosystem or out of the population, we don't want to pull too many out because we can end up crashing that population. This is a massive issue when it comes to especially fishing right now. We're overfishing within the oceans for wild fish. And if you take too many of those fish away, the population can actually crash, in which case it will not survive and they'll all be gone. So this is something that is looked at, especially for a human perspective and for human benefit, is that we don't want to overfish or overhunt, because we will end up basically pulling too many individuals out. We're going to hurt the population growth. It's not going to go fast enough for us to go out and harvest more individuals, and so we end up depleting the population down to pretty much nothing. Now, populations can also oscillate, meaning they can fluctuate, going in cycles. And a really good example of oscillations within a population is the snowshoe hare and the lynx populations. these guys go through a rise and crash in about a 10-year cycle. Now, the reason being is that the snowshoe hares and the lynx, they have a predator-prey relationship. And so what we see, right, is that the hare population will grow. So there's going to be a lot of these, basically rabbits, that are increasing in numbers. And as they increase in numbers, that means there's more of them available for the lynx to eat. And as the lynx eat all these hares, right, they're going to be able to reproduce at higher rates, meaning there's more lynx now. So as the hare population grows, the lynx population grows with it, since there's more food available. The resource for the lynx, food, is now higher. However, they're going to eat too many of those hares, which is going to then limit the hare population. So the hare population drops since too many of them have been eaten. And that means that the lynx population also has to drop because there's now too few hares to support that current population of lynx. And so the lynx population will drop down too. When the lynx population drops down low, there's fewer predators, which means the hare population can now grow. So you see how we're going in a bit of a cycle where every time the hare population or the prey population grows, the predator population grows in response. And in response to that, the prey population drops, which then the predator population drops. So the predator population is basically always following what the prey population is doing.